Hello everyone, my name is Rashin. I'm working for a feed SRE team at LinkedIn. In continuation with the cool talks we have seen so far at SRECon, in this talk I'm going to talk about how robust monitoring powers high availability for LinkedIn feed. So overview, in this I'm going to talk about how the LinkedIn feed architecture works, then what do we monitor, how do we monitor, then high availability for the feed infrastructure, how do we achieve high availability for feed infrastructure, and what are the best practices which we have learned from our experiment. Okay. So LinkedIn, in LinkedIn we have close to 500,000 users, and we are 107 million active users. We have on and off online and offline storage system that handles north of 40 million messages. Now, LinkedIn central data pipeline handles about 1.4 trillion messages across like a 1400 brokers, and we have been seeing a 2 to 3x growth year over year. That brings to the LinkedIn feed. LinkedIn feed is the default experiment for the LinkedIn members. It helps them discover the most relevant content and read original views for the people that matters to them, and they can take part in the unique conversation about the things they care about. Now, how the LinkedIn feed architecture works. So when clients or as a member when goes to the LinkedIn site, they see that our feed system generates a feed for a member upon request by aggregating the content created by the entities. Now here entities can be a member, a school, or things you follow. Whenever LinkedIn members makes a comment or like or any updates, we write to the data source and we ingest that data to the Kafka stream. The data ingestion is done asynchronously through Kafka, and all the timeline data is presented in our feed Kafka stream, which streams all the content on the LinkedIn. Now let's look into the read path, where when the member visit the LinkedIn site, member will have a connections and follow. So our backend system generates a top K results for each entity. Then we apply the relevance algorithm and then serve back the feed to the member. This brings us to the monitoring part, that how do we monitor? We have each component, we have a lots of things to monitor. So we define that by the major like a SRE, Google SRE book, and we also have been using the same methodology. So we look at the load average, we look at the errors, same like in errors we look at a 500 for XX, we look at the timeouts. For load average we look at week over week and make sure that in sudden spike or in sudden drop what's happening. For saturations also we look at the CPU, we have a memory usage, we look at the network, we look at the disk IO and all. On top of it, the LinkedIn also has a similar to AWS containerization, which we call it as a rain. So in that fashion, when we have a more traffic, we can add more instances and scale down. So we also look at that number as well, that matrix. This brings to how do we monitor? What are the tool set we use? LinkedIn mostly use their internal tool set. So I'm going to talk about InGraphs. So InGraphs is a matrix visualization for the round robin databases, and it's a front end for us. Then we use Automatrix. So Automatrix is a matrix collection service. It collects the matrix and then it pumps to the Automatrix. It's similar to Graphite in open source world. Then we have a nurse, which is also a monitoring system which detects a cause and then a way to describe us for remediation and then execute against them. So one of the example is we want to, when let's say processes dies, then what you want to do. So automatically we want that, okay, when process die, I want to restart that process. And we also can tune that okay, if you have a more number of, like if this happens multiple times, then we want to alert that. So you can define all those stuff in the nurse. Then we have our iris. So it's similar to calling service. So all the critical alerts, which are mostly we look at errors or latency, and we also look at a Kafka lag matrix. So these are the like a critical alert. So whenever it passes the threshold, we want the call to goes to the engineer, and we want somebody to look at those services. Now, how do we achieve high availability for the feed infrastructure? So as we have seen in the data source, we have multiple data partitions. So data is distributed across the different nodes. As we can imagine, like okay, in LinkedIn we have so many members, so we have so many member data available. So it's very hard for us to keep it on the single instances. So we have multiple instances we have spread across. In our case, we have a partition to 720 partitions. We came up with this number based on our benchmarking, and it's easier for us for future growth. And then, so that's how this is the number we came up. This brings to like once you have partitioned the data, now anytime when you have any data corruption happen or any node goes down, you are affecting that number of member set of particular subset of the members. So how do you avoid that? In our case, we are using a replication. So we are copying the same data across the 3 replications, and also we have a different colos. So we have for each follow feed system, we have 3 replicas across the different colos. So whenever when you have a data loss or anything, we can have a second replica or third replica to serve the same identical partition. Now, for any distributed system, once you have a replica, now anytime when you want to restore, backup and restore, so that brings like anytime your node goes down, how do you restore that service? So you need a better tool set to support the system. In our case, what we do here is we have a separate backup nodes, and they don't serve any traffic, so that we don't need to have a special dedicated hardware for that. So they are like a standard Linux boxes. It doesn't need to have a special SSDs or anything. And then we have, and for restore, we use Salt for us to restore. So most of our data we store it to the Hadoop, and then whenever one node goes down or anything, we just copy that data from the HDFS, and it's very quick. Now the quota. So how do we? So a lot of time, whenever the suspicion activity happens, like a spammer or anything. So in that case, we are protected by the quotas. So whenever any particular user or member or anything, they exceed the load quota, so that we don't affect the wider audience. So that's how we are saved by the quotas. Next brings to the failover. In event of unforeseen outage, we can easily fail out to that colo and go to different colo. Similarly, we do frequent live load test to check our health of our system, and that also helps capacity planning. I think today in the morning we also had a detailed discussion about failover and live load test. This brings to the best practices. So in order to achieve the availability, the bugs can be introduced anywhere, right, in the hardware or software. So that we have some good practices we follow to maintain high availability. So one of them is automated hardware issue detection. So whenever any node goes down, we don't want to manually interject. We want that whole node to go out of rotation, and then sysops can then investigate what's happening. Then we have A/B testing, which is I think in LinkedIn we call it leaks. So for every new feature deployment, we first ramp to the team, then we ramp to the company, and then we gradually ramp to our members. Then we have proof. Proof is similar to error budgeting, Google's error budgeting. In that case, we have a set of predefined rules. As long as developer teams maintain that rules, they don't violate, then they can deploy anytime they want. We don't bother them. Canaries. That brings to the canaries. So canaries, whenever we do any deployments, we go gradually. So first we have a EI. In EI we deploy our code, then we deploy to the canary box. Canary is a very small set of number users would be affected. So not all the traffic would go to that box. In that way we can detect early failures. Mostly we run our canary and we monitor our canary for 30 minutes to 1 hour, and we have automated systems which in place which validates the error and error latency and all, and in that way we decide that whether this new binary is good or not, and then if it's good, then we proceed with the deployment. This brings to the end to the dark canaries. Now this up to canary part, we have been doing this for a while. Now in recently, like for about a year ago, we started to experimenting with the dark canary, because if you see in the canary that our members, when you have a bad canary, our members are already affected by that. So how do we avoid this scenario? So we have introduced the concept of dark canary, where what we do is we tee the traffic from the source node and production node, and we have a copy to this feed that traffic to the same product node. So in that way, and we don't send the responses back to the clients. So in that way, users won't see any issue, and from our end, we can detect issue much faster. So let's go deep dive into the dark canaries. So as we know that the testing takes time, resources to implement and maintain and execute and analyze the test, dark canaries are used for alternative and relatively low cost to test in prod. So dark canary mirrors the server production traffic and receive the copy of the production traffic, and responses are never sent to the clients. Okay. So dark canary has a major two components. One is the source server, which takes a regular production traffic that takes real traffic, and then it is configured as a dark canary dispatcher. It makes a T of it, copies it, the read request, and redirects to the dark canary node. In also dark canary, the dispatcher node also does the second thing is it uses the multiplier. So it multiplies whether like how much read request you want to forward to the dark canary node. So if the multiplier is greater than 1, then you want to have a multiple copies to send. If it's less than 1, then you want only certain % of the traffic you want to send to. While the dark canary is taking the copy of the production traffic from the source server and running the newer version. So if you look at it here, the clients never see the response from the dark canary. So dispatcher nodes computes their response. It also sends to the dark canary, and when the results comes back, you can validate the both results. So how do we use dark canary for the feed system? So we use dark canary for only read-only request. The read requests are forwarded to the dark canary, and write requests are automatically filtered out. Now because of this, we can also scale this via multiplier. So we can multiply if we want to send more traffic, we just update the multiplier, and in that way, in the dark canary node, we can send more traffic to. And there is no production impact, as that dispatcher node is not going to send the traffic responses back to the clients. Now in this scenario, we want to make sure that the dark canary request doesn't show up in the analytics results. So to differentiate that in analytics, we updated like for a page key, we have a different page key for the dark canary request, and for a tree ID, that is our separate unique ID, we changed to set to 0 so that it doesn't show up in our analytics results. Now how do we use dark canary? What are the advantages we have seen so far? So it made it faster, like a new build verifications. It detects schema changes. So a lot of time we assume that, okay, we have update in Kafka, we are working with different teams, then we request new schema version change, we expect that to be happen, but in reality it's not. So we can detect all that before hitting to the Canary node. New colo certification. This also helped us tremendously. Most in the previous, whenever we build out a new colo, it was extremely difficult without sending the real user traffic. It was hard to detect what are the problems are. In this case, the dispatcher would send traffic to the Dark Canary, and that would be the new colo. So you can easily simulate the read request and make sure that how your system behaves. During this exercise, we also have seen that it really helped us warming up our caches. So in some scenarios where you lose your caches for certain data center, then it's easier to rebuild those caches by sending the read request. So that we also found this very useful. And that brings to the capacity planning. So because now you can send with the multiplier, you can replicate the number of requests. You can test using this as a capacity planning as well. So now this goes to the capacity measurement with Redliner. So we use a live traffic in production environment, and because it's a Dark Canary, there is no visible production impact and minimal overhead because you are not doing anything special. You don't have to write any integration or special test to catch this. So this is a standard our LinkedIn any data services at the bottom stack. We have a load balancer which sends the traffic to. You have a multiple DBs, sharded DBs. Now you have a pick like one data source which would be the act as a dispatcher. You have a separate dark node which act as a Dark Canary. So all the requests, all the read requests from the source node would come. It will redirect to the Dark Canary node. And from there, how we do it is we collect all the raw metrics from that. We have a health check rule where we check the health of the system. We look at latency, error rates, network timeout, system stats. Did we increase any exceptions or anything? So that we checked and we report back to the Redliner. Redliner checks that and makes sure that okay, the system is healthy. Then again, it updates the multiplier. So now this happens circularly so we don't have to intervene. Automatically it runs, or whenever we have a new binaries, automatically it goes to the new boxes without affecting the user. So it's very efficient way to check this. Now what we have found out by this. So here if you look at it, all the blue lines is the source node and the red is the dark node. So if you look at it, standard, mostly we have serving 600 QPS, and then we started to change the multiplier. And if you look at it at about 2.5 hours, you look at the QPS on the Dark Canary node hit to about 2600, and we see the 95th latency increase from 10 to 15 milliseconds. The same thing, you can monitor the system set on the CPU and you make sure that how your system utilization were looked. So at that time we measured that we saw on the dark node about 30% CPU utilization. So these indicates like how much your system can handle. So if your system, and this is the memory utilization, mostly we didn't see much changes from about 45 milliseconds to 50 or 45 gigs to 55 gigs. So safely we assume in our case the system was healthy, and in this way like we can realize that okay, at least if you have a 10 boxes we can support 22K QPS. Now what are the advantages and limitations of the Dark Canary? So the main thing what we have seen is in Dark Canary, if you are running at the very high level, if you are running it at the front end side, you want to be mindful for your downstream services, because when you multiply, it will affect the downstream services. So that's the key thing. If you are running it at the bottom of the stack, then you don't have to worry about it. But yeah. And right now, what we are using Dark Canary is only for the read request. You can also tune it for the write request. But again, in that case, you need to create a separate cluster, and it defeats the purpose, because now again you are testing another set of framework. You are not looking at your actual tech stack. Okay, that's end of it. Cool. Thank you. Question?
Hey, thank you for a great presentation. I'd like to hear about, I'm not sure how complex is your feed services itself, but is there any kind of the consideration between their interaction with other services, whether that will be in-house or external to LinkedIn? Is there any considerations about that?
So for the Dark Canary, so there are a lot of companies use their different methodology. There are also open source tool like a replay. A lot of people use different approaches. A lot of in our case, we use a live traffic. A lot of time you can use a synthetic traffic, or you can replay the log. So there are multiple ways you can achieve this. In our case, we use dynamic discovery, which maintains the state via Zookeeper. So every time when we need to update the state, we can update in the Zookeeper. So whatever your tech stack is, you can tune according to that.
Right. Well, my question is about, have you kind of expanded this effort outside of your kind of area?
So this right now is only, we have been using it for only LinkedIn. We didn't, I think, open source it yet.
Okay.
Yeah.
Got it. Thank you.
Yeah. Okay.
Yes, so in your Dark Canary stuff, I have a forking out request, which is basically you got the front request, you forked it to this Dark Canary side, and then I have my microservices below it.
Yes.
All those will move back to production, right?
Yes, so your downstream will be affected, but so that's why we have distinguished by a separate page key and the tree ID. So the analytics won't see it, but for your downstream services, yes, it will be affected. It will get extra QPS for that, and it will have to respond back to the results. So let's say if you send more, if you tweak the multiplier and you send more requests to it, then your downstream will be affected. Like you will be busy.
Right. And
yes.
Is this open source or? It's
no, it's not open source.
All right.
Yeah, we might do it. Yeah.
All right. Thanks.
Thank you.
How do you factor in the issues about the Dark Canary dispatcher that sits on the source nodes if you have changes happening, since that's production facing, as opposed to doing it maybe above it, with Nginx or a load balancer or something above doing the replication?
Sure. So we have seen the only time the problem we have seen with the dispatcher in our current infrastructure is when the Dark Canary node itself is down. So what we have seen is, because the Dark Canary itself is down, dispatcher try to send the request. Now it is waiting for response. So during that time, your dispatcher node is waiting for that response. So that's the only place we have seen that dispatcher node would behave in production. Otherwise, as long as the Dark Canary node is up, we are good. Because again, we validate through a timeout, so we have SLAs for it. So as long as it doesn't meet the SLA, it's going to drop the request.
Do the Dark Canaries also have a dispatcher? Is it dispatchers all the way down?
No, you don't need a second dispatcher for everywhere. So yeah, it's based on the resource. Yeah. So for your downstream services, there is no dispatcher. It would act as a regular request. Yeah.
How do you validate that the response from the dark service is consistent with the actual response from the real service?
Yes. So we have extended this to custom verifier as well. So we also we extend the Dark Canary to custom verifier. So which sits at the dispatcher nodes. It compares both the requests that, okay, I'm expecting 200 response within this millisecond, and did we get the same response from the Dark Canary as well? And that response is compared, and then we emit the metric so that we can visualize via n-grabs.
So that's done in real time? So when the real service responds, it collects the response and then matches it to the dark one in real time or later on?
It is real time. It's a close to real time, okay. Like based on your alerting system. Yeah. Okay, cool. Thank you. Thank you, everyone.